In about 72 hours, a piece of abandoned SpaceX hardware will slam into the moon at 5,400 miles per hour. Not a meteor, not a natural object, a rocket, one that humans built, launched, used, and then left behind. A hollow aluminium cylinder, the height of a 5-story building, tumbling through space for 18 months with nowhere to go, until gravity made the decision that no human bothered to make. Nobody can stop it. The math closed months ago. And what it leaves behind, a crater, a plume of lunar dust, rising 75 kilometers into the sky, debris scattering across 183 kilometers of the moon's surface, will change how every future mission to the moon gets designed. Because in 3 days, by accident, we are about to run the most important lunar impact experiment in 15 years. This is not a warning. It is not a threat. The moon gets hit by things all the time. What makes August 5 different is that we know it is coming, we know exactly what the object is, we know the moment of impact to within minutes, and 23 scientists across multiple countries have positioned every telescope they can point at the western lunar limb specifically to watch what happens. An accident became a science experiment. And the science experiment is about to answer questions that will matter to every astronaut NASA plans to put on the moon's surface in the next decade. Here is everything you need to know. New here, this channel covers what is actually happening in space right now with real numbers and real stakes. Subscribe. 1 second. You will not want to miss what comes next. The object is designated 2025010D. It is the upper stage of a SpaceX Falcon 9 rocket launched from Kennedy Space Center on the 15th of January 2025. The mission it carried was Dual Firefly Aerospace's Blue Ghost lunar lander and Space's Resilience lander, both headed for separate targets on the moon's surface. The Falcon 9 first stage did what it always does. Fired, separated, returned to Earth, and landed on a drone ship in the Atlantic for reuse. The upper stage did what it needed to do, fired its engine, placed both spacecraft on trajectories toward the moon, then separated and went quiet. Blue Ghost landed successfully on the 2nd of March 2025. Resilience attempted its landing on the 5th of June 2025, but lost contact with ground controllers 90 seconds before touchdown and crashed. The mission was over. The rocket stage that made both journeys possible was, by that point, already in trouble. Standard Falcon 9 upper stages end their lives in one of two ways. Stages from missions to low Earth orbit satellites, ISS resupply, commercial payloads have enough fuel reserved to perform a deorbit burn after separation, sending them back into Earth's atmosphere to burn up harmlessly over the ocean. Stages from missions that require high-energy translunar trajectories, pushing payloads all the way to the moon, use almost all their propellant getting there. They have nothing left for a deorbit burn. They are released with exactly 0 options for what comes next. 2025010D had 0 options. Too fast to fall back into Earth's atmosphere, too slow to escape the Earth-Moon system entirely. It settled into a chaotic high elliptical orbit, swinging between 220,000 kilometers and 510,000 kilometers from Earth, the same gravitational territory the Moon occupies. And there it drifted, unmonitored, while the forces that govern everything in space slowly went to work on it. Earth's gravity, the Moon's gravity, solar radiation pressure, the gentle, continuous push of sunlight on its surface, nudging the stage by fractions of a millimeter per second per day. Over 550 days, those forces combined in a way that orbital mechanics makes inevitable in crowded gravitational environments. They walked the stage onto a path that intersected with the moon. Nobody noticed until September 2025, and the person who noticed was not working for NASA. Bill Gray runs a one-man operation called Project Pluto out of New Hampshire. For decades, his software, specifically Find, Orb, and Orbital Determination, space situational awareness programs at observatories across the globe, they all use Gray's work. He is independent, unaffiliated with any government agency, unfunded by any institution. In September 2025, Gray's software began ingesting observations of 2025010D gathered from amateur and professional telescopes at facilities in Mississippi, Utah, Beijing, and England. More than 1,000 individual position measurements accumulated over months fed into his orbital solution. He ran the numbers, the solution converged to a single answer. The 5th of August 2026, Western Lunar Limb, near Einstein Crater, impact. Gray published the prediction on his website without drama. His comment on the situation was characteristic of the man. The motion of space junk is mostly quite predictable. What followed was not quiet. A team of 23 researchers across multiple institutions mobilized around Gray's prediction. Led by Benjamin Fernando, a postdoctoral researcher at Los Alamos National Laboratory, they published 2 papers, one calling on the global astronomical community to observe the impact, the other modeling the physics of what the collision would produce. NASA confirmed the trajectory and announced that its lunar reconnaissance orbiter, in continuous orbit around the moon, would image the crash site before and after the impact. By the time August arrived, what had started as an abandoned piece of hardware no one was watching had become the most observed accidental lunar impact in the history of space exploration. One independent astronomer in New Hampshire. Over 1,000 telescope observations. A mathematical certainty that the rest of the world then organized itself around. To understand what is going to happen on August 5 and why scientists are scrambling to watch it, you need to understand what the moon actually records and what we can read from that record. The moon has no atmosphere, no weather, no plate tectonics. When something hits it, the crater that forms is permanent. It will be there in exactly the same condition in 1 billion years as it is in a week. Every crater on the lunar surface is a preserved record of an impact the size of the impactor, its velocity, its angle of approach, its density and mass distribution. The moon is, in a very precise sense, the solar system's most complete impact archive. We have been reading that archive for decades. From orbit, from the seismometers the Apollo missions left on the surface, which detected moonquakes triggered by natural impacts and revealed that the moon's upper crust is extensively fractured, shattered by billions of years of bombardment into a porous, highly fragmented layer that transmits seismic energy very differently from Earth's interior. From the craters themselves, whose size and shape tell us about the objects that formed them. But there is a limit to what reading the archive from a distance can tell you. The craters are old, the impactors are long gone. You know what they left behind, but reconstructing exactly what they were requires models with significant uncertainty. What scientists rarely get is an impact where they know the impactor, precisely its mass, its dimensions, its composition, its structure, and can watch the result form in real time and then photograph it immediately afterward. 2025010D gives them that. For the first time since 2009, in October 2009, NASA deliberately aimed a rocket at the moon. The mission was called LCROSS, Lunar Crater Observation and Sensing Satellite. The target was Cabeus Crater, near the lunar South Pole, a permanently shadowed bowl so cold that nothing deposited on its floor in the last few billion years has ever been disturbed by sunlight. Scientists suspected water ice might be there, trapped in the permanent cold. To find out, they crashed a spent Centaur rocket upper stage into Cabeus at high speed and flew a trailing spacecraft through the plume to measure what came up. What came up changed everything. Out of the permanent shadow, out of a region that had not received direct sunlight in geological timescales, the impact ejected 155 kilograms of water vapor and water ice. The LCROSS data, published across 6 papers in Science in October 2010, confirmed definitively that the moon's permanently shadowed craters contain substantial water ice. That discovery transformed the feasibility calculation for a permanent human presence on the moon. Water means drinking water. Water means oxygen to breathe. Water means hydrogen and oxygen for rocket propellant. The moon's south pole, previously considered a scientifically interesting but operationally marginal location, became the primary target for Artemis precisely because of what LCROSS found when it deliberately punched a hole in the dark. One aimed rocket, one set of spectra from a plume, one discovery that rewrote the roadmap for human exploration of the moon. Now, an unaimed one hits the near side, and what it teaches will matter in different but equally direct ways. What makes 2025010D scientifically unusual is not its mass, it is its structure. Natural impactors, meteoroids, asteroids, fragments from larger bodies are dense. Rock, metal, or a mixture of both, with mass distributed relatively evenly through the object. When they hit, the kinetic energy is deposited in a concentrated point, and the resulting crater is a single, roughly circular bowl whose diameter and depth follow predictable scaling laws. 2025010D is a hollow aluminium shell. The Falcon 9 upper stage is essentially a large fuel tank, a thin-walled cylinder that contained liquid oxygen and liquid kerosene during flight, and is now completely empty. The mass distribution is deeply asymmetric. The Merlin vacuum engine at the bottom of the stage is heavy. The tank above it is almost nothing, aluminium skin around empty space. When this object hits the moon at 5,400 miles per hour, it will not behave the way a dense impactor behaves. We know this because of what happened in 2022. On the 4th of March 2022, a rocket body that had been drifting in high Earth orbit for 8 years struck the Moon's far side near Hertzsprung crater. Independent orbital analysis, led again by Bill Gray, traced the object to the upper stage of China's Chang'e 5T1 mission, launched in 2014. When the Lunar Reconnaissance Orbiter photographed the crash site in May 2022, what it found had never been seen before in the history of lunar impact science. Not one crater, two, an eastern crater 18 meters wide, superimposed on a western crater 16 meters wide, together spanning nearly 30 meters in the longest dimension. No, Apollo SIV-B stage crashed into the Moon in the 1970s, left a double crater. No other rocket body impact in the historical record produced one. The double crater implied something specific. Two roughly equal masses, separated along the length of the object, both hitting with enough individual energy to excavate their own craters, which implied unavoidably that the Chang 5T1 rocket was carrying an undisclosed additional payload, something large and heavy attached to its far end that China has never publicly acknowledged. The crater itself revealed a secret the object's operators never disclosed. That is the power of a known impactor hitting a well-monitored surface. The crater does not lie. It records the truth of what hit it, regardless of what anyone says or does not say. For 2022, today, whose structure is fully documented. Falcon 9 upper stage specifications are public. The crater morphology will test whether hollow impactors systematically produce different signatures than dense ones. If the engine end and the empty tank end produce distinguishable craters, the data calibrates models for every future hollow object that hits the Moon, and there will be more. Because every commercial lunar mission that launches an upper stage on a translunar trajectory without a disposal plan contributes another 2025010D to the environment. Benjamin Fernando's team at Los Alamos published specific predictions for what August 5 produces. A crater 20 to 30 meters wide, the length of a basketball court, shallow because the hollow structure will collapse and distribute energy across the surface rather than penetrating deep. A central ejecta plume reaching 75 to 100 kilometers altitude, a lateral ejecta curtain spreading 183 kilometers across the lunar surface, in every direction from the impact point. That last number, 183 kilometers, is the one that connects this event directly to the future of human activity on the Moon. NASA's Artemis program plans to establish a long-term presence at the lunar South Pole, not a flag and a quick departure, a base, crewed rotations, surface infrastructure, power systems, communication relays, science stations, eventually resource extraction equipment, hardware that represents billions of dollars of investment and is not replaceable on any short timeline. The South Pole is where LCROSS found the water ice. It is where the solar illumination is most consistent for power generation. It is where the scientific priorities of the program concentrate. It is also, given the distribution of likely impact trajectories for objects in high Earth orbit, within the zone where debris from an impact elsewhere on the Moon could realistically reach. Fernando's team noted explicitly in their published paper, the maximum ballistic range of resolved ejecta particles from a standard lunar impact is slightly under 1,000 kilometers. That range is large enough to present a meaningful hazard to future astronauts or infrastructure across a significant fraction of the lunar surface. Understanding the actual ejecta distribution from a real impact, one where the impactor's properties are fully known, calibrates the models that will be used to assess risk to Artemis infrastructure. That calibration does not currently exist from real data. August 5 provides it. There is a third dimension to this story that has received almost no coverage. The reason 2025010D is hitting the Moon is not because SpaceX was reckless. It is because there is no law requiring anyone to make a different choice. The regulatory framework that governs orbital debris in low Earth orbit, the FCC's 5-year deorbit requirement, applied to U.S. licensed operators and to anyone using U.S. launch services, covers satellites and rocket stages below roughly 2,000 kilometers. It was tightened from a 5-year standard to 5 years in 2022 after years of pressure from the debris mitigation community, alarmed by the growing density of objects in low orbit. It applies, it has enforcement mechanisms, and operators plan around it. The orbit that 2025010D ended up in sits entirely outside that framework. A high elliptical moon-crossing orbit, reaching 510,000 kilometers at its furthest point, is not covered by any deorbit requirement. There is no international standard. There is no enforcement mechanism. The Outer Space Treaty of 1967 makes nations responsible for their national entities' space activities but it predates the commercial era by decades and provides no specific mechanism for high-orbit debris disposal. SpaceX subsequently adjusted at least one later upper stage, the one launched in November 2025, for the ESCAPADE mission to end up in solar orbit rather than a moon-crossing orbit. That adjustment was not legally required. It was a choice, which means the choice to do it or not to do it is entirely at the operator's discretion. As of August 2026, more than 20 commercial lunar missions are in active planning or development across 8 countries. Each involves a rocket stage, a transfer stage, or both being placed on trajectories that bring them into the moon's gravitational neighborhood. Each generates, alongside its intended payload, an unintended object that will continue moving under gravity long after the mission ends. The US Space Surveillance Network tracks 27,000 objects in low Earth orbit routinely and continuously. For the moon's gravitational neighborhood, the chaotic high elliptical zone where 2025010D spent 18 months, there is no equivalent tracking system, no requirement to register objects, no monitoring cadence, no early warning framework. The fact that we have 72 hours of notice before August 5 is not because of any system. It is because Bill Gray, working alone in New Hampshire, happened to be watching the moon, as Gray wrote on his tracking page, has been getting hit by things for 4.5 billion years. It does not notice one more. But the astronauts NASA plans to send there will notice. And the infrastructure they will depend on for survival will notice. And building the tracking, mitigation, and governance frameworks for the lunar environment needs to start from real data, not models about how objects behave when they arrive. August 5 is one data point. It happens to be a very good one. At 6:35 UTC on the 5th of August 2026, 2025010D will reach the end of its 550-day unplanned journey. It will be traveling at 2.4 kilometers per second when it contacts the lunar surface, 7 times the speed of sound. The kinetic energy it carries, approximately 11.6 billion joules, the equivalent of 2.8 tons of TNT, will be deposited into the moon in a fraction of a second. The rocket stage will be vaporized. The surrounding regolith will be compressed, superheated, and thrown outward. A crater will form. A plume will rise. The plume, dust, rock fragments, vaporized material will climb above the western lunar limb and briefly appear against the dark sky adjacent to the moon's bright edge. That is the observing window, minutes wide, requiring precise timing and sensitive instruments. Telescopes across North and South America, positioned ahead of time by Fernando's coordinating effort, will be watching. The LRO will image the site 7 days later. What the crater looks like, single or double, shallow or deep, symmetric or asymmetric, will test every model of hollow impactor behavior that has been built from first principles and never validated against reality. What the plume carries, its altitude profile, its brightness, its duration will calibrate the ejecta models that Artemis planners will use to assess debris hazards for the hardware they are about to send to the lunar surface. What the crater's existence demonstrates about the moon-crossing debris environment will, if the right people pay attention, accelerate the conversation about whether the regulatory frameworks that govern Earth orbit need lunar equivalents before the first Artemis crew is on the surface. Nobody planned this experiment. A rocket finished its job, ran out of fuel, and drifted into a collision course with another world because gravity does not wait for governance to catch up. But in 72 hours, the experiment runs whether we planned it or not. This channel will be back when LRO releases the crater images. Subscribe, that update is coming.